Hello, my name is Alex Estrada.
My name is Katya Fairchok.
My name is Andrew Feldmuth.
Hi, my name is Andrew Jezik.
My name is Carson Edgerton.
And my name is Claire Pavelka. We would like to welcome you to Interdisciplinary Session 2. Under the advisory of Dr. Hoyen Lee, Dr. Laura Doyle, and Dr. Michelle Parker, we will be presenting our project, a Greywater-Fed Hydroponics system with self-monitoring temperature systems for LEAP schools of South Africa. Our project was planned to be implemented in Jane Furse, South Africa. As you can see in the projected water scarcity map, by 2025 there will be physical water scarcity in South Africa. Water scarcity has negative implications for human health due to a reduction in clean water access, but it also has a large impact on agriculture. In the Limpopo province, where Jane Furse is located, 33% of all households rely on agriculture for their income. Heightened water insecurity reduces the availability of clean water and puts agricultural communities at risk for food insecurity and large income losses. Our hydroponic system is one way to address water insecurity in South Africa.
South Africa. It's a diverse network of regions and provinces, as you can see from the images on the screen. Two of the most significant factors that our team analyzed were water access for use in agriculture and that relationship to household income. As you can see, the regions of Cape Town and Johannesburg have adequate water access and greater than average household income. These are to be expected, given they are large, business, wealthy centers. The more rural and impoverished areas, however, especially the south and the northeast of the country, have significantly less access to clean water, endangering the country's most vulnerable citizens. With the consequences of climate change mounting, the livelihoods of these agricultural households are in jeopardy. Water conservative measures are needed to ensure there is not only enough water to supply the farms, but also to support the basic needs of South Africa's most at-risk citizens.
With the help from the Frugal Innovation Hub on campus, our team was partnered with LEAP 5 High School in Jane Furse, South Africa. LEAP is a collection of math and science-focused schools that cater to economically disadvantaged students across the entire country. Our first meeting with LEAP 5 was in spring of 2019. Raphael, the school's principal, and a handful of students discussed with us their desire for an alternative agricultural garden that conserves water when compared to traditional farming. The students had done some prior research into what they had wanted to learn about and essentially led the discussion with their eagerness to design a system alongside us. We walked out of the meeting with a strong sense of responsibility to make a great system for them. So our role in the project would be to create a physical learning module which both informs about water-conscious farming methods, promotes produce yield, and shows that engineering can be easy to replicate in these students' daily lives. We held weekly progress meetings with them for 3 months so that they could be involved with the design of the system.
The Engineering World Health program is designed to allow biology and public health students to help engineers on their senior design projects and aid them in being frugal, impactful, and culturally appropriate in the communities they wish to work. The common goal of our group was to introduce a system to the LEAP school and have them be primary contributors in its construction and regulation. As Engineering World Health students, we focus primarily on the educational piece of the project. We plan to create a 5-day lesson plan that coincided with the creation of the system and allowed students to learn more about the biological processes at work within it, and about the outside factors that could contribute to the plant growth within the system. The purpose of the project was to give the community an alternative farming method that would combat their specific environmental restrictions. But the lasting goal was to have the community see the project as their own. The educational piece would have helped us achieve this lasting goal and help the LEAP School 5 community utilize the system to the fullest.
We focused our priorities on these 4 problem objectives. Education is the first objective since our system is being built for students at the LEAP 5 school in Jane Furse, South Africa, and we wanted to make sure that our system had plenty of learning opportunities attached to it. We planned on teaching students everything from how the weather could affect the system to how water would be distributed to the plants. We created PowerPoint presentations and manuals, and we planned on sending these to Jane Furse in our place. Additionally, since Jane Furse is located in an area which is especially impacted by water scarcity issues, we also prioritized sustainability. The system utilizes several recycled and upcycled components, and we designed it so that we could use gray water produced in the LEAP school kitchens. This would help reduce the amount of clean water used in the system. Ultimately, the system was inspired by and designed for the students in Jane Furse, and in our meetings with them, they explained to us that they grow a variety of different crops. As different crops required different growing conditions, another of our priorities was to modify our design to be more versatile to accommodate their needs. Finally, this design needed to be replicable in an area with little access to high-tech manufacturers. It therefore needed to be simple, straightforward, and built from materials which can be easily sourced at local stores.
We designed and constructed a comprehensive hydroponic system that would fit with the parameters set out by LEAP 5 High School. In general, hydroponics is a method of growing plants without traditional soil beds. Instead, plants have their roots directly exposed to water or are physically supported by media substrates. Formulated nutrient solutions are delivered to the grow beds through water recirculation systems by a pump. Water runoff found in traditional agriculture is prevented in hydroponics since the system runs on a closed piping loop. Our team planned on building 2 systems, a prototype here in Santa Clara's Forge Garden and a final system at LEAP 5 in South Africa. Our system comprises multiple subsystems that are strategically interconnected in order to provide a successful system. In general, our project layout has 2 types of grow beds, a raft bed and a wicking bed. To prevent these grow beds from high temperatures, we designed a shading structure that would deploy a greenhouse shading material over the grow beds. Since our system uses greywater, we installed a filter that traps fine mulch particles in order for water to be safely introduced to the system. All of these listed components will be discussed in further detail later in the presentation.
Given the objectives from the previous slide, our team set out to research and determine the most effective way to produce a wide range of hydroponically grown crops. Now, the results that separate an effective system from a failed system can only be observed in the time-consuming scale that is the life cycle of a plant. Hydroponics is such an inherently iterative process, so avoiding misdirection and early issues was critical into ensuring the success of a project. After some initial research, we sought out local experts who we could meet with and learn from. The first trip was to Ouroboros Farms in Half Moon Bay. Ouroboros is a very large and a very successful aquaponics farm that is able to maintain its entire 1 acre of grow space with just 2 employees working 2 days a week, 3 hours a day. This farm visit was eye-opening and showed our group the massive potential in hydroponics and aquaponics. So after some trial and error in prototyping in Santa Clara, our team sought the advice of another successful farm, this time in San Lorenzo Valley High School near Santa Cruz. We were amazed to find the garden was entirely student-run and they used similar types of grow beds that we saw earlier at Ouroboros. The last year's aquaponics system at Loaves and Fishes also proved to be a great reference throughout the development of our design.
The design team came up with a list of challenges that our hydroponics system aimed to solve in order for a successful project. And the first was simple maintenance. The whole system needed to be straightforward enough to ensure the longevity of its use, but also challenge the high school students. The second was energy conservation. We wanted to minimize the footprint the system had on the school's resources. The third was heat waves. Upon initial research and talking with LEAP, we discovered that leafy greens specifically in their climate are susceptible to scorching due to the strong summer sun rays. Next was to employ greywater. So LEAP 5 operates on pumped groundwater to fulfill their freshwater needs, and they have an existing greywater catchment system that is used to water a green lawn. And this could be an opportunity to lower the project's water footprint even further. And the last one was ownership of the system. The students at LEAP 5 informed us of a garden club on campus, and this was our targeted group for construction and general maintenance of the system. So a main focus here was to incorporate the students in the building process and leave them with opportunities to run experiments of their own after we left.
Each of these challenges were paired with a specific subsystem to overcome these obstacles. The types of grow beds selected for our system were vital to ensure simple maintenance and repair. Without proper grow bed selection, we endanger the longevity and effectiveness of our project. Keeping the energy costs of our system in mind, we wanted to remove any unneeded parts. With this vision, our team set out to strategically design our plumbing system to be orientated in such a way to only require a single pump for the entire system. To combat the threat of heat waves, we designed a shading structure. Possessing the ability of being retractable, this subsystem provides shade coverage for the leafy greens during daily peak temperatures, while still allowing healthy sun exposure for parts of the day. We also wanted to employ greywater use in order to omit freshwater usage. With this being said, our team had to design a subsystem that would filter the greywater before being introduced to the system. Finally, to encourage ownership of the system, we wanted to provide a subsystem that would engage students and faculty alike. For students, we've created a data logging system where they can personally partake in data collection from the grow beds through the use of a mobile application. The collected data from the grow beds will be used for student-led experiments. For the LEAP faculty, we have assembled building materials for them to use to construct our system throughout their network of schools in South Africa. Each one of these challenges had to be deliberately addressed in a subsystem in order for our project to be successful.
The raft bed is the grow bed which provides up to 96 plants per module. The design uses a simple frame construction with commonly available lumber and no awkward brackets or fixtures. On our site visits, we noticed many of the large commercial farms use the same kind of bed, but rather than being 8 feet long, they were 80-foot long sections. Water is delivered to the raft bed from the nutrient reservoir, powered by a submersible pump on a timer. The raft bed contains the largest volume of water in the system and acts as kind of a buffer as the nutrient-rich water cycles through the system. The water in the bed is approximately 9 inches deep, and on it floats 3/4-inch thick styrofoam insulation boards, which contain 24 holes with a small net pot per hole, which houses the plant. The raft bed is a great piece to our project because it is extremely low maintenance and very durable. The almost 200 gallons of water housed in the raft bed weigh over 1,500 pounds and require careful analysis to ensure that the frame could support this load. A preliminary analysis was conducted, and that indicated that a beam spacing of 16 inches would be acceptable along the floor of the bed. These beams were then supported by two 2x4 girders, which rested on these buried cinder blocks. The ground under the cinder blocks was leveled and tamped to ensure that the raft bed was even, level, and that water would pool up. We later devised a finite element analysis which confirmed the safety of the structure and revealed that the bottom faces of those spanning beams were a critical area. The beams saw the greatest moment, yet still remained comfortably under the yield point. The analysis of the raft bed and the mesh refinement further reinforces that in fact this is a very hardy grow bed, comfortably loaded below its yield point. The raft bed is the first grow bed to receive nutrients from the nutrient reservoir before the water eventually flows into the wicking bed. As seen in the image on the far left, the raft beds can support plants at many different stages in their life. This adaptability is key to our objective of making a system that can grow multiple types of plants simultaneously. In the photo you can see colorful romaine lettuce, butterhead lettuce, and arugula, the smallest one. These seeds are sprouted initially in Khokhar, a loamy media made from coconut fibers. The plants spend about 2 weeks from seed to seedling before they are transplanted to their final destination in the raft. Plants are harvested by plucking them from the raft and trimming them at the stalk. Our first harvest of lettuce took approximately 50 days, from seed to harvest, which is about 50% faster compared to lettuce that grows in the soil. The raft bed, it's a very ideal system to fill the needs identified by our client, the LEAP 5 High School. The ability to grow a variety of leafy greens gives the students at LEAP 5 or the gardeners at the Forge the tools to explore a wide range of hydroponic growth. The raft bed is the perfect, quintessential high production, high density grow bed, and is even better when paired against the more versatile wicking bed, which the water then flows into next. The wicking bed is a crucial piece in our system because it allows the gardeners to grow more longer-lived fruiting and flowering vegetables. Broccoli, tomatoes, peppers, even potatoes. This is the greatest strength of the wicking bed and why it complements the raft bed so well. Because there's no deep anchoring substrate in the raft bed, light leafy greens are really the best option because heavier plants as they grew larger would collapse. The deep soil and clay ball blend, however, allows plants with longer lives to receive the support they need and produce a successful yield grown in the wicking bed. On the surface, the wicking bed may appear just like a normal raised garden bed, but it uses an actually unique delivery method for the water. Instead of watering from the top of the soil, which allows a significant portion of that water to go unused due to evaporation, water is delivered through the bottom. A perforated pipe spans the entire length of the planter base and then wicks up to the roots. The wicking phenomenon is a result of capillary action, which delivers water from the more water-saturated areas in the lower layers through the soil upward to the deepest roots of the plants. This ability to deliver water straight to the roots from the bottom with no evaporation both conserves water and helps the plants grow quicker and larger. The wicking bed relies on a multi-layer system to deliver water from a shallow reservoir at the bottom of the bed up to the plant's root systems. The layers are needed to protect against the destructive anaerobic zones caused by perpetually wet regions that do not get exposed to oxygen. These anaerobic regions will release a foul smell and cause root rot, which will kill the plants. As seen in the side view image, there are 4 distinct layers. There's a loose gravel reservoir constantly submerged in flowing water. There's a weed mat to prevent plant roots from entering the reservoir, but allowing water to permeate. And then there is a thin layer of sand that adds an additional redundant inorganic separation layer to again keep the soil out. And then lastly, there is a large expanded clay ball and soil compost section. The clay balls are great because they're very light and they keep the soil in the bed from becoming hard packed under the weight of the soil. This hard packed nature would discourage the capillary action, which is the wicking which gives the water to the plant's roots. In the Forge Garden, this grow bed was housed using a thick plastic bed donated by the Forge Garden. But in South Africa, our team will utilize a series of old bathtubs. Leap 5 has great access to discarded or otherwise unused materials, and these bathtubs are perfect because they closely fit the dimensions of that existing Forge Garden bed.
In order for us to minimize our energy usage, we needed to calculate the best pumps to use in each system. It is neither good for our energy usage nor for our hardware to use a pump which is unnecessarily large or small for the kind of flow rate needed to sustain the system. Taking into account the volume of water in each system, the head loss due to system components, and the flow rate necessary to deliver nutrients to the plants and prevent mosquito breeding, we found that the best pump sizes were a 400 gallon per hour pump for the Forge system in Santa Clara and a 1,000 gallon per hour pump for the much larger system in South Africa. We also needed to prevent leakage as much as possible, both to make sure that the plants are getting the nutrients they need and also to prevent unnecessary water waste. Additionally, we wanted to minimize loss of pressure, lack of adjustability, and difficult maintenance. We experimented with several different kinds of seals before settling on using bulkheads for flat, rigid surfaces and uniseals for all other surfaces. Both are relatively easy to install and maintain, and both can easily withstand the pressures present in our system. Uniseals are also very affordable, so in the event that any of the seals wear out, they can be easily removed and replaced at a minimal cost. Using a single pump for the system essentially cuts monthly operation costs in half for system circulation. Additionally, it makes maintaining the system easier since there is only one pump to maintain. By adjusting our design so the majority of the system operates using gravity, this was easily attainable. Also, by adding a timer, we also reduced the costs and the energy needed for the system. The timer cycles the system enough to keep the water moving at the necessary rate without wasting energy and potentially flooding the system. Should the timer or the pump need to be shut off for any reason, the ball valves are placed in the system such that the grow beds can be isolated from the reservoir.
While benchmarking and researching for our project, we noticed an issue with the previous design. In November, we toured an aquaponics system at Loaves and Fishes in San Jose. The farmers wanted us to know that the current growth, seen in the photo on the left, was all that they could grow since mid-April. With more investigation, we discovered that these leafy greens can easily bolt due to inadequate climate. We researched that an adequate temperature range for leafy greens were from around 60 to 80 degrees Fahrenheit. With this information, our team wanted to ensure that the system we produce would be able to mitigate this issue as best as possible. Keeping this problem in mind, we decided to implement a shading structure above the raft beds to keep the leafy greens in the ideal temperature range. Understanding that leafy greens require both direct sunlight and reasonable climate to grow, our shading structure will be retractable to provide direct sun exposure for parts of the day while protecting the vegetables during daily peak temperatures. Our team conducted a thermal analysis on various greenhouse shading materials to determine which percentage of shading porosity would be adequate for the leafy greens. The chart shown on the right shows the material with the higher percentage shading coverage decreases the amount of heat transmitted to the surface area of the grow beds. With this being said, our team determined that a 50% shading material would be adequate for protecting the leafy greens in our system. Our team wanted to prototype 2 different types of shading systems, one manual and one automatic. The manual shading method shown here was determined to be the method deployed to South Africa, while the automatic system would be prototyped here at Santa Clara Forge Garden. We created the manual system because we wanted to ensure that our deployed system could be easily maintained, reducing the amount of electronic components that were ultimately needed for the automatic system. Without the risk of technical failure, we were confident that we could deploy a shading structure that could be manually operated. The structure itself consists of ABS weather-resistant piping, which are stabilized through concrete footings. This frame-like design allows access to the grow beds from all sides of the system. Metal cable is used as a railing guide to prevent the shading material from drooping down and interfering with the grow beds below. When constructing our manual prototype, we were very deliberate on making sure that our manufacturing process could be easily replicable in South Africa. Moving on to the automatic system, we now can see that the shading structure removes the human dependence factor and is now being driven by inline stepper motors. This motorized system alleviates the duty of monitoring the hydroponic system throughout the day. While the automatic system would be ideal, it was not feasible for manufacturing in South Africa. This is how the automatic shade method would operate. Through the use of an Arduino, we connected a temperature sensor to the surface of the raft bed to constantly monitor their temperature. When the sensor reads a temperature out of suitable range, chosen as 80 degrees Fahrenheit, the Arduino would then send a signal to the stepper motors to rotate and deploy the shading material shown here. To ensure that the motors would be able to supply an adequate amount of torque, calculations were conducted to properly size the stepper motors. The main structure components remain the same as the manual system, and only add electronics for the material to deploy. Zooming in a little closer to the motor components of the structure, it was decided that we needed to mount the motors in a safe and effective way. In order to confirm that our mounting design would be satisfactory, we conducted a stress analysis on the ABS pipe that the motors were mounted on. We believed that these were the most critical points that could potentially fail. To ensure that the motors would not jeopardize the structural integrity, we conducted a stress simulation of the ABS pipe. Using SolidWorks, we constructed the section of ABS that would hold the motor through 2 bolts. We refined the mesh around the bolt holes to observe if they were going to have any structural failure. We tested a plethora of loadings that simulated different types of external forces. We came to the conclusion that the ABS would be able to withstand an external load up to 140 pounds, with the actual shading material and motors only weighing approximately 18 pounds in total.
Essential to the success of the project was to conserve water, so why not repurpose it? We identified an opportunity to use LEAP's existing greywater catchment system as our water supply for the hydroponics garden. In general, greywater refers to any wastewater that does not contain any fecal matter. In LEAP's case, the captured water from a dishwashing sink is used to irrigate a green lawn on campus. Knowing that this greywater would contain harmful soaps and surfactants, we designed a simple filter that could be added to the existing system. The mulch retention greywater filter shown is designed to treat 200 liters a day, which is an estimate by the LEAP students of their daily lunchtime water usage. We estimate that the hydroponics garden will need to replace about 1/2 of the total water volume each month due to evaporation and evapotranspiration of the plants, so about 1,000 liters. A T-branch is used to redirect greywater to water the existing lawn, as mentioned, if the hydroponic system does not need to be topped off that day. The filter uses a repurposed bathtub and impermeable baffles to promote water circulation and maximum surface contact with coarse mulch. A mesh sediment strainer at the end of the filter catches fine mulch particles that exit with the effluent. So why use mulch? Initially, a constructed wetland and vertical bioretention filter were tested to determine their effectiveness. The bioretention's slow infiltration rate was not ideal, and the constructed wetland would remove nitrates and nitrites from the water that could be a source of nutrients for the growing vegetables. So by suspending the greywater in just mulch for at least an hour, the undesired soaps and oils present would be soaked up. We ran water quality tests for 2 weeks and averaged the values in the chart as shown. Our biggest parameters to decrease were pH, hardness, and alkalinity. The mulch filter effectively decreased each parameter as shown on the right and brought the water closer to the optimal growing parameters. Once added to the hydroponics garden, the filtered greywater would be diluted and suitable for use in the system. Using data from our prototype's first harvest in the forage garden, we compared water savings from our hydroponics garden to a baseline raised bed soil garden. We assumed the soil garden had an equal grow area and would be watered at a 4-inch depth every 4 days. And so we also assumed the hydroponics garden would need to replace 1/2 its total water volume a month using the greywater filter. So as a result, the water savings projection shows our design using 1/2 the water to produce over 2 times the produce yield.
To promote straightforward construction of our team's subsystems, we have created step-by-step assembly manuals. Each subsystem is taken from just raw materials to a finished product in 10 steps or less through these clear visual guides. No words are needed. These guides can easily be interpreted regardless of language or educational background. The manuals were partially created because every subsystem depended on very fast-paced construction at this rural high school in South Africa. Through the use of simple geometries and locally sourced materials, we have emphasized the need for manufacturability in our design. We believe these manuals are critical to the Leap 5 community or any others who choose to make their own successful systems from our guides. On the left is the original storyboard of our raft bed manual, and on the right you can see the finished product.
A cost analysis was conducted to compare the 2 types of gardening. Both gardens' capital and monthly operations and maintenance costs were projected for 10 years. Only the raft bed's design was considered for this analysis, as this was the only complete harvest our team had. Total yield per year was evaluated, assuming $1.25 per head of lettuce. With a payback period of less than a year and a half and a return on initial investment of 83%, the hydroponics garden is more economically feasible than its soil competitor. One of the main reasons for this is the grow area associated with hydroponics. Our raft beds can grow 4 heads per square foot at 6.6 ounces, while a Cornell University study we compared it to found their lettuce to grow 1 head per square foot at 9.9 ounces.
In order for the students to know what temperature the raft beds are at any given time, they need access to a live thermometer reading. Furthermore, since part of the educational aspect includes the students experimenting with the shade to see how it benefits the plants, they also need to be able to see the extreme temperatures which the plants are experiencing day and night. Using the Blink app development tools, we put together a live temperature reading system, using a waterproof thermometer which will be attached to the raft beds at all times. The circuit includes a Node MCU Wi-Fi chip, which broadcasts the temperature reading over Wi-Fi to the Blink app, accessible by downloading the app and scanning the QR code shown here. Students in Jane Furse can see live data as well as a simple histogram of the most recent values. However, to be able to analyze the data, they need to be able to manipulate the graphs to label the critical values. We set up the app such that a user can export the raw histogram information to a template Excel spreadsheet which automatically adjusts the axes to appropriate ranges and adds callouts for the maximum and minimum temperatures experienced by the plants. The students will create these graphs on a weekly basis, and they will then be able to see trends in the data which might affect crop health.
For the educational component of this project, we had 3 learning objectives for LEAP 5 students. 1, to understand the impacts of climate change on human and plant survival. 2, to understand how the hydroponic system functions and be able to independently maintain it. And 3, to empower students to make a positive impact in their local communities. To accomplish these learning objectives, we plan to implement a 5-day educational program featuring lectures, experiments, and daily hands-on interaction with the system. Each day we covered a topic related to biology or environmental science, then connected this back to hydroponics. At the end of the educational program, we plan to have LEAP 5 students become certified ambassadors for their new hydroponic system. The educational component of this project is critical as it ensures both the longevity and the adoption of the hydroponic system into the wider Jane Furse community.
Our hydroponics project aimed to minimize the use of fresh water and utilize sustainable building materials while still providing a successful vegetable garden for LEAP 5. We achieved these goals by implementing a greywater system, sourcing materials locally, and creating a diverse structure for a wide variety of plants to flourish in our system. Although we won't be able to deploy the system ourselves, the LEAP school will be able to build it without us, using the manuals and instructions we created, and it will be an excellent educational tool for the Jane Furse students. This way, the school will be able to implement a sustainable hydroponic system to benefit the wider Jane Furse community and contribute to a more sustainable agricultural system. We would like to thank Xilinx, the Frugal Innovation Hub, and the SCU School of Engineering for funding our project. We would also like to thank Brent Woodcock for his assistance in assembling the shading structure, Catherine Ronthelier and Thomas Hayashi for their agricultural expertise, LEAP 5 and Headmaster Raphael Mukachi for their collaboration and enthusiasm, and everyone else who helped make this project possible. On behalf of our entire team, thank you for coming to our presentation.